Alrighty, welcome to 16D Euler's form. In previous videos, we said that we always want to write a complex number z in Cartesian form, which is a plus bi form, unless we were writing it in modulus argument form or polar form, unless we were writing it in this brand new one called Euler's form, which we're going to see in a minute is e to the power of I theta. This is the final form for complex numbers. Don't worry, there's no more after this. And this is my personal favorite for a variety of reasons. The first of which is just that it has the number e is back, and it's playing with the number I. This is amazing, and you'll see why shortly. So the first question is, how do we even get into this form? How do we show that e to the I theta is equal to cosine of theta plus I sine of theta? And the answer is, you're going to trust me on it. Sadly, for this proof, you're going to have to wait until we get through most of the option calculus topic for me to justify for you why this is true. So we're just going to go with it, all right? So e to the I theta is always going to be equal to cosine of theta plus I sine of theta. Here's an example for us to look at really quickly. So we have the complex number 1 plus I. This is our Cartesian form right here. We transform this into polar form. Down here, it's got a modulus of root 2, and the angle of rotation is pi over 4. So we're going to write that in Euler's form. Is the root 2 is going to hang out because there was no mention of a modulus here, so there's no mention of a modulus there. We're assuming that it's 1 in the blue box. So the root 2 just gets carried over, and then we're going to write e to the power of I times pi over 4, or whatever, pi I over 4, however you want to write it. All right, so this is just a new way to write things. Let's see what we can do with it. Actually, I guess before we see what we can do with it, we should just make sure we can translate back and forth with it. Okay, so e to the power of I pi. This is, man, I'm going to cry. This is one of the most beautiful numbers ever. E to the power of I pi, by the rules that we've set forward, this is going to be equal to cosine of pi, which we know is -1, plus I times sine of pi, which we know is 0, which means that this is equal to -1. And this, oh man, this is called Euler's identity. And man, if you look up like most famous equations ever, this is always like number 1 or 2 on the list. God, oh God, it's beautiful. It's so good. We've got an irrational transcendental number, e. You probably don't even know what a transcendental number is. That's okay. We've got e raised to a power of I, an imaginary number, times another irrational number, transcendental number, pi. And the answer is just a -1. I mean, it's just... so many important mathematical constants all in one, and it's so concise and just, okay, I gotta stop. Moving on to the second one. We're gonna do this one the same way. It's gonna be cosine of pi over 3, so that's gonna be 1/2 plus I times sine of pi over 3, which is gonna be root 2 over 2. There you go. And then for the last one here, e to the -I pi over 2. I like to bring that negative into the pi over 2, so this is going to be cosine of -pi over 2, which is the same as cosine of pi over 2, which is 0, plus I times, okay, this is sine of -pi over 2, which is the same as negative sine of pi over 2, and sine of pi over 2 is 1. So that's just going to be -I. This number here is definitely 3. I don't know what I was thinking. Okay, next, can we prove these results from the last video using this new form? So we did in the last video by changing cis form into Cartesian form, but can we make sense of it using Euler's form as well? Well, certainly. So cis theta is the same as e to the I theta, and then cis phi is e to the I phi. And if I'm going to multiply those two together, that just means I'm going to keep the base and then add those arguments together using just properties of exponents. And then transferring back into cis form, yeah, that's going to be cis of theta plus phi. So that's pretty straightforward. So Euler's form is pretty nice for certain operations. That's very good. It would be the same thing on the right, just with a quotient. So I'm not going to go through that one now. So now we're going to find the angle of the argument of each of these complex numbers. And our answers will be in terms of theta, okay? Because the original complex number, its argument is just theta. Don't know what it is. So our answers will just have a theta in it here as well. So for the first one, root z, well, that's the same thing as z to the power of 1/2. And since z is equal to cis theta, using Euler's form, this is e to the I theta to the 1/2, which is the same as e to the I times theta over 2. So the angle here, the argument, is theta over 2. For letter B, I already know the answer to this because we've talked about this problem in both of the prior videos. I know that when I multiply a complex number by I, the angle should increase by pi over 2. So I am fully expecting this one to be theta plus pi over 2. Let's now justify that using Euler's form. So this is going to be I times e to the I theta. But what is I as a complex number? We've talked about that before. I is the same as cis of pi over 2, which is the same as e to the I pi over 2. So I have e to the I pi over 2 times e to the I theta, which is going to be equal to e to the, adding those two together, factoring out the I. Here we go, pi over 2 plus theta. There it is. That's how I can get my angle of rotation increased by pi over 2. So there's a third way to justify that. Very cool. For the third one, starting off with a negative I in the beginning. So negative I, that has just a rotation of 3 pi over 2. So that's going to be cis of 3 pi over 2 times z squared. But z squared, using the same reasoning as we saw over in the first problem, is going to be e to the I 2 theta. Putting these two together now, we have e to the I 3 pi over 2 times e to the 2I theta. Adding the exponents together, factoring out the I, we get 3 pi over 2 plus 2 theta. That's great. Another acceptable answer would have been e to the I times 2 theta minus pi over 2. And for this last one, here we have a quotient. So I, we've seen enough times, I is e to the I pi over 2, and we're dividing by z, but z is just defined here as cis theta, when cis theta is the same as e to the I theta. So we're dividing two numbers that have the same base, so that just means we're going to subtract the exponents. So that'll be e to the power of I times pi over 2 minus theta. So the new argument is pi over 2 minus theta. Just a quick moment to talk about I, because it's a very curious number, and we used it quite a few times in the last problem. So thinking about I in polar form is, it's fine. If we accept this idea of cis theta, then sure, I could be equal to the cosine of pi over 2, which is 0, plus itself I times 1, which is a sine of pi over 2. So this identity seems very straightforward. I is equal to I. Great. But using Euler's form, we have I is equal to e to the power of I times pi over 2. And this one, it seems a little less obvious. Is there a way to algebraically verify that this is true? I mean, you could try taking the ln of both sides, but that won't get you anyplace particularly nice. One idea is to try to look at solving x is equal to e to the pi over 2x, and then graphing this to try to find out what an answer is. And of course, it's not going to get you anything good. Clearly, there's no real number solution here, and the two graphs do not intersect. And yet, there is a complex solution. The solution to this equation is I. And there's no direct way that I'm aware of to verify it from this version of the equation. Perhaps you can enlighten me if you can come up with a way that does not rely upon using polar form first, or using the secret mathematics that justifies the connection between polar form and Euler's form. I don't think there's a way. But as I said, you'll just have to wait for that other proof of just a few more months for us to get up to it. Okay, curiosities aside, let's just look at a few more. We're asked to evaluate these, and most of these require a calculator to do something with. So e to the I, the angle of rotation here is 1, so this is equal to cis of 1, or cosine of 1 plus I times sine of 1. I don't know what cosine of 1 is, nor should you. And this is radians, of course. So you'd grab a calculator, make sure it's in radians mode, and you calculate the cosine of 1 and the sine of 1. You pump it in there. Whatever you get, there's your evaluation. The second one is a little bit tricky. How do we deal with 3 to the I? I need that base to be e, otherwise I can't really do much. So let's make the base be e. Forgetting about the I for just a moment. 3 is equal to, using some identities from logarithms, it's equal to e to the power of ln of 3. Right? Because the e and the ln are going to cancel out. So now if I raise both sides to the power of I, we got 3 to the I is equal to e to the ln of 3, all to the power of I. Of course, raising a power to a power just means that we're going to multiply the two powers together. So we have e to the I times ln of 3. And now my argument for this complex number is ln of 3. So we work out cosine of ln of 3 plus I times sine of ln of 3. Whatever that is the answer. Great. Now this third one, I to the power of I, an imaginary number raised to an imaginary power. We could approach this one in the same way as letter B. We could rewrite I as e to the ln of I, and then have this all raised to the power of I. And rather than do it that way, I will actually link to a video that will take this approach. So you can check that out down below for one of my favorite, actually I'll link to 2 videos. 2 of my favorite math channels have done videos on this problem. So I'll let you take a look at those. The way that I'll do it is, I think, at least a faster method that is going to rely on what we know about I already, which is that I is equal to e to the power of I times pi over 2. And we're going to raise this whole thing to the power of I. So we're going to multiply those together. I times I is -1. We get e to the power of negative pi over 2. And that's a real number, about 0.208, which is pretty cool that we can take an imaginary number to an imaginary number and get a real number. That's awesome. I think that's really neat. As for letter D, this is just going to expand upon that. So rather than seeing I to the I squared, let's rewrite that as e to the negative pi over 2 to the I squared. And if we bring in that I, then we'll have e to the I times negative pi over 2 squared. But what is e to the I times negative pi over 2? That's a complex number whose argument is negative pi over 2. And that number is negative I. So now I have negative I squared. And negative I times negative I is just equal to -1. So that was a very complicated looking question with a very simple answer. And of course, if you didn't like the methods that I showed you, or that the other 2 videos that I linked to showed you, if you want the shortcut to figure out what I to the power of I is, just head over to Wolfram Alpha and ask it, and it'll tell you what it is. It'll tell you that it's a transcendental number, which is a word that I used earlier. Very cool. It'll give it to you as a continued fraction, something that I've seen IAs written on before. That's neat. We've got a multi-valued result, so this is kind of hinting at the fact that there's actually infinite answers to this problem, which again is touched upon in the YouTube videos that I'll link to. And this is even related to the exponential image on a Felix Klein curve, which I have no idea what any of that means. So Wolfram Alpha, just full of fun, interesting mathematical vocabulary for us to explore. Anyway, that's the end for 16D. 16E is going to tie in very nicely with this topic. So buckle up. It's coming at you soon.